So roughly today I'll be talking about the work I did in 2012. And this is with Professor Erhan Kozan and myself. So it's about earthworks and how to do it efficiently. So luckily there were 4 publications from this work, so that was very, very good for us. Particularly the bottom 2 in very strong journals. Mostly today I'll be talking about the work that's in this paper, but first I'll talk about the initial work in this one here. So when I talk about earthworks, we're talking about moving earth rocks. Golf courses. These are called linear infrastructure projects because they have length. They can be quite wide, meters worth of construction activities, particularly railways and roads. The main innovation of the work is a graph theoretic approach, and I'll get to that in the second part of today's talk. So we start off with the terrain, the countryside as it is. This is my biggest case study, which is certainly. But the idea was to take this land and then build a nice smooth road for it. So everything above the road will have to be cut away. And if the land is not high enough, then we actually have to raise it to get this desired shape. Now those 2 charts can be seen more clearly in this one. So this is the profile of the road in red, and the blue is the current terrain. So everything above, for example, this big bit here has to be chopped away. Go and bring in earth and material from certain exterior places, but the idea is to do it is to use what we have here, not to actually go and get earth elsewhere. However, in practice, if you have an imbalance, for example, you have too much earth or not enough, then you'll have to do something with that imbalance. Now, after looking at what other people have done with these situations, I came up with a strategy which uses the elevation within those sections. So what you actually do is moving things left or right. By using 3D blocks, we can actually model the elevation and do more sophisticated modelling. So in this case, blocks are either movable objects or they are containers of earth. They have a position which you know, a size, and you also know what's within the block typically. By introducing these blocks, we have inherent cutting and filling precedences. That means that we know the sequence of parts within a given stack. There's lots of advantages from using blocks. We can model the terrain exactly the same. Now the earthwork walls are actually, well, they can be measured in many different ways. So in this work we use a filter cut. The reason for this is that that metric is generic and it takes into account the major factors, which is the gradient and the physics. In practice, many different types of machinery is used from week to week, from day to day. So you cannot really create a plan for a specific type when that type of machinery is always changing. So if we have a generic measure, then that solution is capturing the main difficulties, which is the gradient. So the idea is to take that domain and split it up into lots of little blocks. So the red ones are the ones that we need to cut, and the blue ones is where we need to fill. And then once we've actually got a solution, we actually need to display it to someone. So these are two Excel tools that were initially created. So in this one here, we actually have an animation which actually shows you the sequence of where you actually cut and fill to, with arrows pointing. Now the other one is a pseudo 3D chart. This one actually is a top-down perspective. So these numbers show you the elevation in this one. A better approach is a fully 3D approach. So I'll just show you how that works. So this is a software called Google SketchUp. It's actually linked to a program called Voodoo, so you can actually program directly into it. So what I've done here is to actually code up how to drop blocks into. I also had to show you the path between the cuts and fills, and that's the green line that turns on and off. The idea, this is quite a small case study, about 44 blocks. So there's a sequence of 44 cut fills. Movements. And eventually the idea is that you've actually flattened it. Every time you make a decision, you change the terrain surface and hence change the cost of moving between any 2 points. So that's one of the main innovations and complexities of this problem, to be able to actually capture that. Okay, so 3 different approaches were developed. The first 2 are mathematical approaches to do basic planning. The first model move those fractional parts to different areas. Now the third approach is the most powerful of the three because it models the terrain elevations and the changing costs of haulages. The first two models assume a static cost. The first two approaches had to be performed because that was part of the project and with our partners from Swinburne University. And I knew straight away it wasn't going to work, it wasn't going to be as good, but they're still useful. And lots of good things came from that as well. But definitely the third model is the best. So these models are not overly complicated, but they do require lots and lots of information. Now, that information, if you could actually compute it as you need it, everything would be fine. But LP solvers, in particular CPLEX software, requires that you have all that information already computed, which is a big issue. So as you make the blocks smaller and smaller and increase the number of them, it becomes really, really difficult to actually generate the models. So you run out of memory very quickly. But if you can actually generate the model, it actually solves quickly. If you can actually build that model on the computer. Now, if you run out of memory, what happens is that there's a little bug in CPLEX which most people don't know about. It actually loses all the memory that it takes. So I had a lot of problems solving these problems because of their size, and after 1 year, I found I'd lost 200 gig of my hard drive. So that was rather nasty. I had to actually go back and manually get it back. It took days and days and days. And there's a little line on the CPLEX website which says this, but they don't really tell you. So it's a good bit of information to know, actually. I'm not sure if they fixed it yet or not. I don't think they have. But I should also say Sam's computer broke and he was running his model lots of times with CPLEX. So quite possible it does a lot of damage to your hard drive. But that's just a guess. This is the first model I was talking about. Lots of conditions about where you move things. H here is a binary variable between two types of blocks. The objective function is the emissions, so it's the fuel consumption by the number of trips by a binary variable which tells you whether you're actually making the trip. The second model is simpler because it's got continuous variables. So Q is the amount that you actually move, and you can select that. And again, a number of constraints which say how much you can move or not move. If you're solving 3D problems using the conventional models, then you can actually subdivide the domain into cross-sections, work out the solution for a particular cross-section, and then replicate it across the domain. That was tested and worked actually very well. So you don't actually have to model the full 3D nature of the problem. So with the first two models, you can see that the difference between the work metric and the conventional distance metric is quite great. Now the work metric models the elevations, whereas the distance is only kind of left or right. So you can see that there's huge reductions in the fuel usage and the cost required to do these earthworks. And as you increase the number of blocks, you can also get superior solutions. So for example, we can compare 66,000 to 99,000 just by changing the block size. These results here show you how many hauls you need to do the cutting and filling. And if you look at these distances, that's an awful lot of mileage for the trucks that actually do the hauls for these types of problems. slide shows the replication of 3D domains into different cross-sections. For example, where there's 1 cross-section, 2 or 4. So I'd like now to talk mostly about the superior approach, which is this one, the graph theoretic approach. So the terrain is modelled by a digraph, a directed graph, and the shortest path between the current cut and fill blocks is identified using that graph. The shortest path value is recorded and the graph is updated to reflect the new terrain. All of the arc weights refer to the cost of haulage between different points. Because a work metric is used, some of the arc weights can actually be negative, and that poses quite a lot of trouble. So to get around the negative arc weights, we need to do scaling. And this allows us to use the best shortest path algorithms like the A-star algorithm, which is very, very quick. And also the digraph can be partitioned in a time-based way, and distributed programming can be used to utilise or to dynamically reduce the computation time. So the graph looks like something like this. Every node refers to a stack of blocks. So a stack is, one block on top of each other. In particular, X, Y, and Z. The graph is built so that the actual node weights are the current elevation of that stack. All of the arcs refer to linkages, and if there are no arcs, it means that you cannot move between those two stacks at that point in time. But you may be able to later other conditions. Now, the two grey nodes are the source of the cut and the fill. So the idea is to go through the cut path between those 2 points, and that's shown by the red dashed line. Once you do that cut and fill, you change the node weights, and you have a new terrain surface from which you then can compute more path and more haul. This is the technical details of how the graph is constructed and some of the calculations that are required. So we have to work out Euclidean distances, forces, work, angles between different inclined planes. The graph consists of a set of nodes and a set of arcs. And the solution to our problem is a sequence of cuts and fills. So it's a sequence of pairs B and B prime, where the first one is in the set of cuts and the second is in the set of fills. Now, the optimisation model for this entire problem is shown here. But the main thing to actually see is the fact that the objective function is not made up of static costs. It's made up of costs that change for every decision you make. For me, this is the first problem I've ever seen in which that has actually occurred. In every other optimisation problem I've ever solved, the costs have always been static. So it didn't matter what decisions you made, the cost of doing anything in your problem was always fixed. This one is not like that at all. Now consider the fact that we might have thousands of cuts and fills, so we have to actually solve separate shortest path problems thousands of times. The nice thing about the graph approach is that any infeasibilities which actually violate the cutting and filling precedences can actually be fixed using the graph. Now this occurs because the graph will only evaluate haulages from the current elevations within the graph. So if you specify the wrong elevation, it doesn't care because it will go from the correct one in the graph. So all you have to do to correct a solution is actually to record the actual data in the graph. So there's no complicated kind of correction strategies required here. So basically what I mean there is that you just have to specify the stack where the cutting and filling occurs. You don't actually have to tell it where the elevation is at that point in time. This slide here demonstrates an infeasible solution where you've actually told it to do a sequence of cuts and fills which are not possible because you cannot actually get to the blocks at that point in time, either because there's something else in its way or it's sitting in mid-air levitating, for example. So actually by evaluating it, this solution is actually translated into a feasible solution, which is the one below here. Now to actually solve the optimisation problem, you know, we've got the graph, the structure to actually do it. We actually need a variety of different techniques. And these techniques are unconventional. So we have a constructive algorithm to build a starting solution, and then we need many refinement techniques like simulated annealing, evolutionary algorithms to actually improve it. And to actually evaluate every refinement, we actually need to do lots of applications of the shortest path algorithm. And we also need to update the terrain constantly. There's always resetting the terrain, evaluating it, and putting it back again, and doing those types of calculations. So as I was saying earlier, the arc weights can be negative. Now there's only one algorithm to actually do a shortest path algorithm with negative arc weights, and that's called the Bellman-Ford algorithm. Positive, then you can use faster, more general techniques. However, scaling is not a valid thing to do, theoretically. The problem is that if you scale arc weights, then arc weight, or paths of different lengths are scaled in different ways, and it's not proportional to each other. In fact, you don't actually get the right haulage costs. So for example, scaling affects longer paths more greatly, and paths with fewer arcs are identified as shorter, and paths with more arcs are deemed longer. And this creates inconsistencies in the costs. However, there is a way around this, and we have proved that scaling is consistent on grid-like structures. So in a generic directed graph of no particular structure, you cannot prove this, but on a grid structure you can, and it does work. Now we can work a static minimum arc weight and use that to scale all other arc weights. And these are the calculations that are required to do that. So what that means is that all arc weights can be scaled directly at the point that you need to do the evaluation. And you can do this in an efficient computational way. So scaling is always consistent on a grid structure for the work metric, so we proved that in the paper. The work for a longer path cannot be made smaller than that of a shorter path, which is very good also, because all we need to do is to compare paths of the same size in order to determine the one that is smallest. So we don't actually compare paths of, say, 10 links with a path with 15 or 20 or another value. We only look at the smallest number of links. Now, as the number of evaluations increases, the computational burden is very, very great. So if we can actually do a parallel evaluation, then computation time comes down dramatically. So a few opportunities actually exist to do that, but there is one which is fortunate. So that involves a temporal decomposition. In that approach, we create multiple service graphs and evaluate each part in parallel. And these different subgraphs are initialized at different points in time. So all we have to do is actually to define correct node elevations and update the arc weights in an appropriate way. So very fast algorithms were done to accomplish this. So in essence, what we do, if we had 4 processors on the computer, we would actually split it up into 4 different subgraphs. subgraph would be the first 25% of the cuts and fills. At that point in time, the train would look in like a certain way, with certain elevations and things. So that would be the priming state for the second graph. At that point in time, we would then prime the third graph, and then we do the same for the fourth graph. And evaluations work out those costs, and at the end, we'll then add them together to give us the total cost. Now, to actually solve the optimisation problem, we used two hybridised techniques. Because this is an integrated problem, it makes the problem so much more difficult to solve. So when I say integrated, I mean we have three separate decisions that have to be made. And they are decide upon. So conventional meta-heuristics will not work because the search space is just too complicated. To get around this problem, a dedicated improvement phase has to be introduced to actually get good convergence. And we have block sequence and block assignment perturbation to actually refine the solution. Now the search strategy is special, and it's described here. So the idea is very much based on kind of a military perspective where you actually parachute out of the plane, for instance, land somewhere. So what you do is drop down, you're looking around, is this area good or not? You make a judgment call. If it is, then you spend time to actually look around in detail in that area for the best point. Now, if your judgment call says that this is a rubbish area, you go and move somewhere else. You don't waste the effort to actually look in that area. So this actually is very similar to the taboo search strategy, which does a comprehensive neighbourhood search. But it's also like simulated annealing because it has a kind of stochastic element throughout in some way. It actually combines the best of both techniques. And of course, you can make a move and then go back if that move is not good. So about 3 or 4 months worth of numerical investigations were run around the clock. This happened last year. MP was used for the parallel computations. Some of the problems were quite quick to solve, but the largest one, the 7K one, was I think 15 hours without parallel computations. And all of these techniques were run for the different objectives, either the distance or the work metric. The top table here is a summary of the different case studies. Cut fill pairs. So that's quite a large sequence. You know, for every one of those cut fill pairs, we have to decide on where this is cut and where it goes to, and that sequence is rather large too. The block size is roughly 50 metres. I mean, we could have gone smaller, but then that would have made the problem even bigger again. So from a practical point of view, 50 metres is fairly reasonable. Maybe if you remember out here when they took the building down and they had the earthworks there, you think about 50 metres, it's quite a good size for planning purposes. Now the graph of the largest one had about 570 nodes. about 3,600 arcs. So you have to actually evaluate shortest path problems on that graph. In fact, there's 1,500 times. Every time you want to get one solution, you have to do 1,549 shortest path problems on that graph. That's a lot of work. Now this table is more interesting than the other two because it shows you the speed up from the parallel evaluation, how good it actually is. So for example, the biggest problem takes 56,330 seconds. That's on a 4-processing machine. As well. In fact, the 2 up from the bottom we get, or 4 up, is 61% reduction. So that's really, really good. So in summary, the evolutionary strategy was quite good, well, probably the best. Gave the best solution, but CPU times are very, very poor. The simulated annealing approach is still really the best, and it can be extended far more easily, and the solution quality is quite comparable. The parallel evaluations are highly successful, which means that we can solve more realistic sized problems and make this work is more realistic and useful to practitioners. There are still some room, well, there's a lot of room for improvements. Even though these results are so good, in the course of doing this work, a whole set of new ideas arose. Before I actually tell you those, I'll just summarise these points here. This problem is difficult because it has a dynamic objective function, so there are non-static costs. It's an integrated problem, so there's 3 parts to it. The parallel processing saves between 40 and 60% of the computational effort to solve the problem. And this allows us to solve superior real-size problems. But by doing some of these things here, we can actually do even better. Now, if we re-evaluate only certain parts of the solution that change, then we don't have to do a full re-evaluation. Unfortunately, I did not see that at the time, so all the changes made by the heuristics actually assumed a complete re-evaluation. But by doing this, the speed up could be quite phenomenal. There are algorithms which actually work out the shortest path on graphs that change. So those techniques could have been applied, and that could actually achieve an even greater speed up. In this problem, we looked at movement of blocks as whole entities. However, we can also split those blocks up into fractional parts. Now, to do that in an approach would be even better again, would achieve even better solutions. But then you would actually be introducing a 4th decision variable. So you would have an assignment, a sequence, pathing, plus the actual identification of the actual amount of a material you're moving. And if you look at real projects, you can do cutting and filling concurrently. So many things can be done at once, not just one set of things at a time. So that would be also very novel. I was cutting here and cutting here at the same time and doing that all at the same time. Or you could actually define how many cuts and fills you're actually doing. So to finish my talk this morning, I'm just going to show you some pictures of some real-life projects. So it was actually fairly obvious to me, but some practitioners in the field, they were actually not very happy with them. I actually had to prove to the engineering community that, in fact, yes, you can use blocks and it is reasonable. And the perfect example of that is actually down here when they took the building out. As you can see, we took out this, took this photo from the window, and they've actually cut away a block. I mean, it's very clear, clearly defined block. So it does happen, and it is reasonable. Fortunately also, very close to where I live, across the road actually, they built a Bunnings and then an Aldi. So there was a hillside which looked like that. That's what it looked like before. And they chopped the trees down, but it's very nice, green, wet, cool. So the idea here is exactly what my earthworks is about. You have a hill which looks like this, and you want to raise it up, so at the bottom end to build shops. So you actually have to cut the top away and move it down the hill to the bottom. Now this site is about, I don't know, between 300 and 500 metres long, about 300 metres wide. And the elevation difference is probably 100 metres from top to bottom, so it's an awful lot of work. And most of the cost was probably spent by the Bunnings organisation, so we're talking about $50 million, something like that, over an entire year to do this. So this is at the top end, so you can see it's a mountain and it's hard rock. They had to drill for 6 months straight to cut that away. And what they do is actually they spray paint on the ground where they're going to do the cutting and filling. You can see the pink lines here. So once they do some cutting, they actually put the earth or whatever next to where they've done the cutting as a pile. Then they bring in trucks and excavators and bulldozers to actually move it. So that is, in essence, a block's worth of rock. This picture is fantastic because, again, it shows you blocks. They've actually come and taken out blocks all the way down. So there's a sequence of cutting and filling there. And eventually, you know, they come straight down the hill, straight down vertically. This is showing you all the activities happening in the middle area. So everything at the top here has been cut away and slowly moved down and processed. So in the middle here there's all topsoil because that's used later on because it's more valuable than the rock. So they crush up the rock and then use that in the lower levels first and they bring the topsoil back. These piles are quite interesting because what they do is they kind of transport it in trucks and they unload it and then the truck kind of moves along dumping. So you get these kind of long kind of hill-like structures and then they bring something across the top and flattens it. This is the end product. So nice and smooth, so you can build a huge big Bunnings, which is really good for me because I can just pop over and buy stuff every week. Now this is probably after, I think, 8 months of processing to get it smooth like that. So we're talking about filling, compacting, digging up again, filling, compacting, smoothing, watering, all sorts of activities. This is the lower end where they actually did the filling, so they actually had to build a big retaining wall to actually kind of above the road. So you actually drive up through here. So nothing was there originally. Shows you the upper side, kind of how steep it is, and kind of how they actually moved it with the trucks of different types. And they kind of created haul roads, mini haul roads within the site to actually do the movements. Okay, that's all, folks. I'm glad to take any questions.